Hi, everybody. Welcome to Lecture 30. Yes, that is me in my bobblehead version that my wife thought was hilarious for my birthday last year. What do you think? Does it look like me? Kind of scary. Kind of scary. So, today's class is going to be on amazing epoxides, and they are amazing. You'll just have to wait and see how amazing they are. I'm also bringing you a broadcast live from a different room. This is a different room in our house. A little variety to mix it up. Also, I apologize if the sound is different. I'm trying a different set of microphones / headphones. That's what these little guys are. So hopefully you can hear me just fine. If not, please let me know. Whoa, bobblehead. So, amazing epoxides. These are in section 10.10. There's a lot of, they're just amazing. And I want to show you how amazing. So, let's get to it. What's so great about epoxides? So what I want you to notice is this is an actual epoxide, this little three-membered ring with an oxygen attached to it. It is very cool because if you notice the reactions we can do with it, actually put an OH group, a hydroxyl group on your molecule, and any nucleophile / base. But what's really cool, besides putting two functional groups on your molecule, is you get to choose which carbon of the epoxide, which one of the regio centers on this molecule do you want the nucleophile / base to end up on? You have choice, and choice is power, okay? And then at the end of our little video today, we'll throw in a little flashback to E1 and a slightly different E1 reaction that is in 10.13. I'm not sure why they just waited all the way till then, probably because they want you to go back and play with it some more. So we'll take a look at that. All right. What we want to do is try to open these epoxides up with a nucleophile / base. And so why would they want to open up? Let's just make sure we're clear about this. The ring opening of epoxides is a little unique in that we're dealing with a leaving group that you have never seen before. They're hence new leaving group. But it shouldn't surprise you, okay? Because this oxygen is partially negative. So it is sucking electron density away from the two carbons of the epoxide and making these carbons partially positive. Okay? So we have an ability here, if we have a partially positive carbon, those are electrophilic carbons that are fodder, perfect for a reaction for a nucleophile to come in and attack at some point with these electrophilic carbons. Okay? And therefore, once we get an attack with a nucleophile, we can't make a fifth bond on those carbons, so we will have to open up the epoxide ring. That's the general gist of what these epoxides are all about. So to open up these epoxide rings, there are, as you saw, two possible reactions in our table from the last slide. Let's look at these two possibilities and how they take place. Please feel free to slow the video down, repeat any part of this slide that's coming up. A lot of chemistry is happening in these next couple slides, so I'm hoping you review them often. Scenario number one, you can take a strong nucleophile and strong base. So either one, but most importantly, if it's a strong nucleophile, you're going to be under basic conditions because you're going to have a negatively charged nucleophile. So no acid is present. And therefore, this nucleophile is going to look at this epoxide, and there are two regions of the epoxide that it could be interested in, right? We have this partially negative oxygen. Oh, sorry about that, partial. But we also have this tertiary carbon. Whoa. And this secondary carbon. We have these two regions of the epoxide that are very unique. So let me show you again up close and personal. Here's our epoxide, okay? And notice the epoxide is living up here with the oxygen, and we have these two carbons that we could live in. We have the methyl sticking out at you on this side, and the hydrogen sticking out at you as a wedge on this side. Notice there's no rotation about this three-membered ring. It's very sterically hindered. The top has the oxygen. So the only place that this nucleophile can attack is from the bottom. So we have stereochemistry that's going to happen here. And that means we are going to go a la SN2. There it comes. SN2 is going to take place because we have a really strong nucleophile. But the region that this molecule can get attacked by is only the bottom. So the regiochemistry is going to come from the backside attack, like all SN2s do, a backside to the leaving group. Okay? Now, if I do a backside attack, and I'm doing SN2, and I have two different regions in this epoxide, I have a secondary carbon region, and I have a tertiary carbon region, right? So which region do you think this nucleophile wants to attack if it's going to do an SN2 reaction? Right. Yep, the less hindered carbon. That's where SN2 reactions wanted to take place all the time. Why not have it happen here? So yes, this nucleophile is going to take its lone pair and attack this secondary carbon. And in doing so, from the back, it pushes up the hydrogen and the methyl and opens up this epoxide, giving this oxygen, which is already sucking electron density away, pulling up that charge and breaking it, giving it the lone pair. Whoops, come back. Sorry, technical difficulties. Giving it the lone pair, not a bond, and creating this beautiful looking alkoxide. And so we've added our methoxide to the backside on the secondary carbons region. Stereochemically, notice we've made a chiral carbon. That's to come. But what's going to happen with this O-? It's not happy. So it can do one of two things, and we can do one of two things in the lab with this O-. We can either add, now that the reaction's done, we can add an acid to protonate that O. It's called an acid workup, is the fancy name for it in orgo. Or you can let this O- just attack the solvent that is swimming in this reaction, which is the conjugate acid to the methoxide base. So it will find a proton anywhere and become an alcohol. And that is how you can add a nucleophile slash base to the less substituted carbon and put the hydroxyl group that finally ends up from the epoxide, pops out on the more substituted carbon. So it's very SN2 in its fashion. It's stereochemical fashion here. As a review, you can see the nucleophile is always going to attack the less hindered carbon. And you're going to get inversion of stereochemistry, essentially meaning it's just a backside attack. Okay? So there's a lot of stuff going on here. Feel free to review this slide over and over and over. Okay. So what about scenario 2? What if I don't have a strong base? Or I don't want a strong base. I don't want the SN2 attack. I don't want my nucleophile on the less hindered carbon. What if I want my nucleophile on the more hindered carbon? That region of space. What if I want it over here on this tertiary and not on the secondary? So these are regions of the molecule, so we call this regiochemistry. I want my nucleophile on the tertiary. And I want my hydroxyl group to end up on the less substituted carbon in that region on the secondary. Okay? Now, a little side note. If there's no difference between the two carbons, they're both secondary, the regions of space are exactly the same, then you will get a 50-50 reaction to each one. Okay? There's just the nucleophile / base / weak nucleophile will never be able to tell the difference between the two. So it'll attack it both equally. But notice my example is a tertiary versus a secondary. So we have two totally different regions of space. And now the chemistry is in an acid solution. The first step is always plus loves minus, and we got a weak nucleophile. So we're not doing SN2 attack at all at this point. We are going to let this oxygen fall in love with that hydrogen and become protonated. So it becomes a protonated epoxide. And now you have one of the worst things that oxygen can ever feel like. You have a protonated oxygen that's positively charged. Oh my God, if you thought that oxygen was pulling electron density from the two carbons before, now imagine how much it wants those electrons from the two carbons. It's pulling them drastically. It wants a pair. Give me a lone pair back. I don't want to be positively charged. So, which carbon could it pull the electrons from the easiest? Which carbon could end up feeling more positive than the other one and be okay with it? Kind of sounds like positive charge. Kind of sounds like which carbon can handle positive charge. Hey, that kind of sounds like SN1 regiochemistry. Which region of the molecule can handle a positive charge better? Yes, the tertiary carbon. And so what happens in this epoxide is it starts to slowly open up even without a nucleophile. These bonds are starting to break, and as you can see, it's pulling electron density a lot easier from the tertiary carbon. This is much easier to do because that tertiary carbon doesn't mind being as positive. So now with a weak nucleophile present, just if that carbon's losing a pair to this oxygen, it's trying to go, then if that's trying to go, then now I can add my weak nucleophile and it can come to the rescue. Not as O-, not as a strong base, but just as a lone pair to help out this carbon and attack at the more substituted carbon. So regiochemistry, the weak nucleophile will attack the more substituted carbon. But notice, stereochemically, how's the stereochemistry of this attack look? Yes, it looks very, very SN2. It's still stereochemically attacking from the backside of this epoxide. So we will still push and produce stereochemistry that's SN2 in fashion. We will still get this to come up, and H+ will fall off of this molecule because we hate to have an oxygen with a hydrogen and a positive charge. So this mechanism should be fairly straightforward for you by now. We've seen it all over the place. When alcohols act as nucleophiles, they lose H+ at the end of the mechanism so that they can retain their beautiful two lone pairs and become neutral. So in the overview, really, it's important to recognize that when you have acidic conditions in a weak nucleophile, that you're going to protonate the epoxide and do kind of attack at the SN1 carbon. That region of the epoxide that will be allowed to be more partial positive. So it's very SN1 regiochemistry. but it is very SN2 stereochemically. It still has to come from the backside because that oxygen's kind of occupying the top half of that molecule. So there's no way even the weak nucleophile can come from the top. It still has to come from the bottom. Okay? And therefore, we call this as a borderline SN2 attack stereochemically on an SN1 electrophilic carbon regiochemistry. Wow, pretty cool. All these attacks in stereochemistry and chirality, and you can tell I am madly in love with epoxides because they can put two functional groups on my molecule that I can live in Orgoland and then go make other things with them. So they're very popular starting materials. Let's see how you do on this one. Please take a second and see if you can write the correct stereochemistry as well as regiochemistry for these two epoxide opening reactions. 4, 4, 3, 2, 1. Okay. Did you come up with these answers? This is going to take place, and notice I color-coded the oxygen so you can see which oxygen ended up on which carbon. This is a strong base, good nucleophile OH-. So notice it's attacking the least substituted carbon, the secondary carbon. And the epoxide opens up and ends up becoming an OH group on the more substituted carbon, this tertiary benzylic versus this secondary aliphatic. So as you start to do the process, I highly recommend that you label these right at the beginning of any epoxide you have to make sure you can see the difference in the regiochemistry. So you make sure that you have your attack occur at the correct carbon. Bottom one, ready? This is what I got, okay? Now, I'm gonna protonate the epoxide first, and then it's going to start pulling electron density away from the more substituted carbon, making it easier for the red oxygen in my water molecule to attack the more substituted carbon. So this is an SN1 attack that ends up producing SN2 stereochemistry. So it still has notice there's still chirality involved, which is really strange for an SN1-like attack, but that's the beauty of epoxides. And just to practice, figure out R and S for these chiral centers. And are these molecules meso, diastereomers, enantiomers? It's all coming together, all flying together now in Orgoland. So, see if you got this answer. I got for the chiral centers, drum roll please. Sorry, I don't have the sound effect for that. That had to be your drum roll. I got S and R and S, which means that these two are enantiomers. They have their chiral centers, both chiral centers exactly flipped. So you can do a lot of really cool chemistry with epoxides, and notice this is one epoxide, but not necessarily the only epoxide for this molecule. I could have had the epoxide as dotted lines, not just wedges. All right, again, let's practice, practice, practice. Let's play with this one. Try to determine the major product in this reaction and see if you get the same answer I do. Ready? 5, 4, 3, 2, 1. Okay. So, as you do this reaction, notice this again is under acidic conditions, which means I'm going to protonate this oxygen right away, and it's going to start pulling stuff away. This is a methyl, and so I have a tertiary, and I have a secondary. If that oxygen's pulling charge away, which carbon of the epoxide is going to be more positive? Yep, you got it. That tertiary carbon, okay? And so that tertiary carbon is going to get attacked by this weak nucleophile. And it's going to be stereochemically coming from the bottom, pushing this bond open onto the other side, keeping the epoxide OH on the top. And so if you saw A as that final outcome, you are on the right track. A is correct. This is the final product to this reaction. But I threw a wrench in here. Once you make A, this bond can rotate, can spin. And so what I want you to notice is that if I take this molecule, I've built it here with the OH coming out, the methyl is a wedge coming towards you, right? The OCH3 is this little guy, red, black, and I'm putting it straight down in the same plane as my OH. So OH, carbon, carbon, OCH3. These are all in the same plane with a methyl wedge coming out here and a methyl wedge coming out at you here. So this is the same as that molecule. Oop, let's see if we can see it here. So there's the red plane, plane, okay. Now, what I did is I took this OH, and if you take this OH and I pull it back, so it's away from you now, and put the methyl group in the plane of the screen, the paper, and I take this this OCH3, right? And I push it out towards you and put the ethyl group in the plane of the paper. So now I have a methyl, carbon, carbon, ethyl. These are all on the plane of the paper. Then notice what now I have is an OCH3 coming out as a wedge at you and a white little hydrogen coming out at you. Two little wedges of an H and an OCH3. Do you see this molecule here? This also looks like compound D. D is also a correct answer. It was just rotated. Whoa, tricky. Sorry. So D is also correct, which means woohoo! E is the actual correct answer with A and D as both being identical. And if you have doubts, determine R or S for these. These are chiral centers, and no amount of rotation of the molecule will ever change R or S. Okay? All right. Awesome. Okay. Oh. Now,
it's astounding. Time is fleeting. Madness takes its toll.
uh-oh. Look out!
Listen closely.
Not for very much longer.
I've got to keep control.
I remember doing the time war, drinking those moments when the blackness would hit me and the void would be calling. Let's do the time war again.
Let's do the time warp again.
It's just a jump to the left.
So, this is, sorry, I couldn't help it. That was my Rocky Horror Picture Show kind of, woo! If you haven't seen it, gotta go see it at least once. At a midnight show, no less. All right, this is a blast from the past. It is the final thing I want to throw at you today. It's just a little subtle E1 reaction. And I think you might be able to figure this out because you're now becoming Orgoland goddesses who can spy any plus loves minus reaction and just figure it out without having to memorize them. If I were to give you this reaction and ask you to tell me what the products would be for this reaction. My hope would be that you would not have to go look at section 10.13, 1013 in the textbook and make sure you found it, or have it on a flashcard somewhere, or make sure you had it memorized. My hope is that you would look at this oxygen like we've had in the past. And we've always added acids to protonate these oxygens to make them better leaving groups. So if you just get an acid, any kind of good acid, H2SO4, H3PO4, these are good acids for this reaction because of one thing. Their conjugate bases are not nucleophilic. You know what I mean? What if I were to throw HCl at this? That's a good acid. But we'll come and look at this in a second. HCl might not be the kind of acid you want to use to do this. I want a non-nucleophilic acid, something that gives me just a lot of H+. And when I heat it up in a lot of H+, my water is going to get protonated. It's going to fall off. Why? Because I put it on a tertiary carbon. So there's the E1. It'll just fall off, create a carbocation, and there'll be no nucleophile. Yeah, the water could act as a nucleophile there, but what would I make? The same starting material. So no nucleophile present. And every so often, without a nucleophile, we know then this reaction would do an E1. And it will still follow Zaitsev's rule. Remember Zaitsev's rule? The more substituted alkene, that's the alkene that will be made in this E1 reaction. They call it a dehydration because one of the products you spit out here, you lose water. So water's kicked off. And it's therefore dehydrating your molecule, making it very thirsty. Lost water, help. Okay, sorry, I get carried away. All right, what if though you did use HCl? Then what you're doing is actually you're adding Cl- as well as H+. And so not only are you protonating your alcohol, but you're putting in a good nucleophile. And if you happen to forget to turn on the heat, or even turned on the heat, it doesn't matter. You're going to get SN1 as well. You have a nucleophile in here, and the problem, oh my God, it's just the ugliest thing. You end up getting both products. Ah! So try not to use this form of an acid if you want to generate only your alkene. Okay? These acids, sulfuric, phosphoric, are much better to use for a dehydration lab. All right? Cool. So I thought I'd throw a little challenge out there, but not necessarily answer it in this video. Woohoo! This is my hook for you to come back to the next video. Before the next video, please try to show the products from these two reactions. And also try to show the reaction mechanisms. Show me how these reactions actually took place. And if there's any stereochemistry, please feel free to determine R and S so we can compare notes in my next lecture when we come back to it. Oh my God, it's scary, Nick bobblehead. Oh, sorry. It is kind of scary. All right, no more Nick bobblehead, I promise, I promise. I hope you're feeling good. I hope everybody you know is feeling good. Please stay safe, and I'll see you next time. Bye.